Let us discuss UV spectroscopy. This is the last unit, Unit 5 in spectroscopy. UV spectroscopy or ultraviolet visible spectroscopy, abbreviated as UV-Vis, is an analytical technique that measures how much ultraviolet or visible light a molecule absorbs to determine its chemical composition and concentration. UV-Vis spectroscopy is a type of absorption spectroscopy that studies the interaction of light in the ultraviolet and visible regions of the electromagnetic spectrum with matter. It involves measuring the amount of light absorbed by a sample at specific wavelengths, which is then used to identify the presence and concentration of different substances within the sample. The technique relies on the principle that molecules absorb light at specific wavelengths, which corresponds to electronic transitions within the molecule. UV spectroscopy is widely used for the identification and quantification of analytes in various fields. The specific wavelengths of light absorbed are characteristics of the substance, allowing for its identification and quantification. Let us discuss the origin of UV spectra, laws of absorption, Lambert Bouguer law, Lambert Beer law, molecular absorbtivity, transmittance and absorptions. Introduction to UV spectra. Spectroscopy is a measurement and interpretation of electromagnetic radiation absorbed or emitted when the molecules or atoms or ions of a sample move from one energy state to the another energy state. UV spectroscopy is a type of absorption spectroscopy in which the light of ultraviolet region, the range is between 200 and 400 nanometer, is absorbed in the molecule, which results in the excitation of the electrons from the ground state to a higher energy state. The term electron spectroscopy encompasses the excitation of electrons by ultraviolet or visible radiation. Hence, the UV-based spectra belong to the molecular spectra. A technique is used to study the concentration and type of sample based on the absorption of the electromagnetic radiation. UV spectroscopy. UV spectroscopy is concerned with the study of absorption of UV radiation, which ranges from 200 nanometer to 400 nanometer colored compounds. It absorbs the radiation from 400 nanometer to 800 nanometer in the visible region. Colorless compounds absorb the radiation at UV region. In both UV spectroscopy and visible spectroscopy, the valence electrons absorb energy and thereby molecules undergo transition from ground state to excited state. This absorption is characteristic and it depends on the nature of the electrons present in the valence shell of the compound. Origin of UV spectra. UV spectra arise from electronic transitions within atoms and molecules that absorb ultraviolet and visible light. When a molecule absorbs UV or visible light, electrons are excited from their ground state to higher energy states. The specific wavelengths absorbed depend on the molecule's electronic structure and the energy differences between these levels. Explanation. Electronic transitions. UV spectroscopy is based on the absorption of UV and visible light, which causes electronic transitions within molecules. Excitation of the electrons. When a molecule absorbs a photon of UV or visible light, an electron is excited from a lower energy level, that is ground state, to a higher energy level, that is excited state. Molecular structure. The wavelengths of UV and visible light that a molecule absorbs depend on its electronic structure and the energy differences between its electronic states. Types of transitions. Common types of electronic transitions that contribute to UV spectra include pi to pi star, N to pi star, and sigma to sigma star. Chromophores. Specific functional groups within a molecule called chromophores are responsible for absorbing UV and visible light. Intensity and wavelength. The intensity and wavelength of the absorbed light provide information about the molecule structure and concentration. The origin of UV band structure. For an atom that absorbs in the ultraviolet, the absorption spectrum sometimes consists of very sharp lines, which brings out the fact of a quantized process occurring between two discrete energy levels. For molecules, however, the UV absorption usually occurs over a wide range of wavelengths because molecules normally have many excited modes of vibration and rotation at room temperature. In fact, the vibration of molecules cannot be completely frozen out even at absolute zero. Consequently, a collection of molecules generally has its members in many states of vibration and rotational excitation. The energy levels for these states are quite closely spaced, corresponding to energy differences considerably smaller than those of electronic levels. The rotational and vibration levels are thus superimposed on the electronic levels. A molecule may therefore undergo electronic and vibrational rotational excitation simultaneously. Because there are so many possible transitions, each differing from the others by only a slight amount, each electronic transition consists of a vast number of lines spaced so closely that the spectrophotometer cannot resolve them. Rather, the instrument traces an envelope over the entire pattern. What is observed from these types of combined transitions is that the UV spectrum of a molecule usually consists of a broad band of absorption centered near the wavelength of the major transition. Electronic transitions. In UV spectroscopy, the electronic transitions occur when a molecule absorbs light, causing electrons to jump from lower to higher energy levels. What we call this is molecular orbitals. This process is the foundation of UV spectroscopy, providing information about the molecule's structure and electronic properties. The absorption of light by a sample in the ultraviolet or visible region is accompanied by a change in the electronic state of the molecules in the sample. These two words have been repeated. In the electronic state of molecules in the sample. Generally, the most probable transition is from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. The energy differences between the electronic levels in most molecules may vary from 125 to 650 kilojoules per mole. The energy supplied by the light will promote electrons from their ground state orbital to higher energy or excited state orbital or anti-bonding orbital. The absorption of light energy by organic compounds in the visible and ultraviolet region involves the promotion of electrons in sigma, pi, and n orbitals from the ground state to the higher energy states. Any molecule has either n, pi, or sigma or combination of these electrons. These higher energy states are described by molecular orbitals that are vacant in the ground, or unexcited states are called antibonding orbitals. Many molecules containing electrons that are not directly involved in bonding are called non-bonding or N electrons and are mainly located in atomic orbitals of oxygen, sulfur, and halogens. The antibonding orbital associated with the sigma bond is called sigma star orbitals, and that associated with the pi bond is called pi star orbital. As the n electrons do not form bonds, do not form bonds, there are no antibonding orbitals associated with them. The presence of an electron in an antibonding orbital clearly indicates that the molecule is in the higher energy state. Identical functional groups in different molecules will not necessarily absorb at exactly the same wavelength. The energy change for a particular transition dictates the position of the absorption of a given group. Transitions in identical functional groups in different molecules will not necessarily have exactly the same energy requirement because of different structural environments. Types of electronic transitions. Several types of electronic transitions are commonly observed in UV spectroscopy. Sigma to sigma transitions. Sigma electron from orbital is excited to corresponding sigma star antibonding orbital. The energy required is large for this transition. For example, methane has CH bond only and can undergo sigma to sigma star transitions. It shows absorption maximum at 125 nanometer. The next transition is pi to pi transition. It involves pi bonding electrons moving to pi star antibonding orbitals, often found in conjugated systems. Compounds containing multiple bonds like alkanes, alkenes, carbonyl, nitriles, aromatic compounds, and so on undergo pi to pi star transitions. The examples are given as alkenes generally absorb in the region 170 to 250 nanometer. N2 sigma star transitions. Saturated compounds containing atoms with a lone pair of electrons like ONS and halogens are capable of N2 sigma star transitions. These transitions usually require less energy than sigma to sigma star transitions. The number of organic functional groups with N2 sigma star peaks in the UV region is small, 150 to 250 nanometer. N2 pi transitions. They involve non-bonding electrons on atoms like oxygen or nitrogen moving to pi star antibonding orbitals. Compounds containing double bond involve heteroatoms. Involving heteroatoms, C double bond with O, C double bond, triple bond with N, N double bond with oxygen undergo such transitions. Then N to pi star transitions require minimum energy and show absorption at longer wavelength around 300 nanometer. So this is the pictorial representation of possible electronic transitions are shown here. So we have sigma, pi, and n here. Those levels are here, and sigma and pi they refer bonding levels, and n is non-bonding. Pi star and sigma star are anti-bonding levels, and the transition is see sigma to sigma star. This is the larger one. The energy transition for sigma and sigma star are larger compared to other transitions. And this line refers sigma to pi star, and this line refers to n to sigma star, n to pi star, and n to pi star and pi to pi star. Clearly, the energy required to bring about transitions from the highest occupied energy level in the ground state to the lowest unoccupied energy level is less than the energy required to bring about a transition from a lower occupied energy level. In all other compounds other than alkanes, the electrons may undergo several possible transitions of different energies. The principal characteristics of an absorption bands are its position and intensity. The position of absorption corresponds to the wavelength of radiation whose energy is equal to that required for an electronic transition. So this is the possible transition in different organic compounds like sigma to sigma star transition that will take place in alkanes, sigma to pi star in carbonyl compounds, pi to pi star in alkanes and carbonyl compounds, alkenes, and so on. N to sigma star in oxygen, nitrogen, sulfur, and halogen compounds. sigma 2, pi star in carbonyl compounds. Key aspects of electronic transitions in UV spectroscopy. Excitation. UV spectroscopy involves exciting electrons within the molecule. Electronic states. The excitation process leads to transitions between different electronic states, including ground and excited states. Quantized energy levels. Electronic transitions occur between distinct energy levels within a molecule. Absorption. The absorption of light at specific wavelengths corresponds to the energy difference between these electronic states. The last one is molecular orbitals. These transitions often involve electrons moving between bonding and antibonding molecular orbitals. The next title is The Laws of Absorption. One is Lambert Bouguer law and another one is Lambert Beer law. Almost the amount of energy absorbed or transmitted by a solution is proportional to the concentration of solute. So we look into Lambert Beer's law. This law states that the amount of light absorbed is proportional to the concentration of the absorbing substance and the thickness of the absorbing material. The absorption is directly proportional to the concentration of the solution of the sample used in the experiment. The absorption is directly proportional to the length of the light path, which is equal to the width of the cuvette. So cuvette is the length, this is the width in which the sample will be kept. It's like a rectangular glass piece, cuvette. In simpler terms, the more concentrated a solution and the longer path of the light, the more light will be absorbed. So the law is often expressed as absorption A equals sigma BC, where A is the absorption, sigma is the molar absorptivity with the units of liter per mole per centimeter, B is the path length of the sample, C refers the concentration of the compound in solution expressed in mole per liter. So this is mole per liter concentration. And minus di by dc, which is directly proportional to I. So as per the definition, minus di by dc is directly proportional to I. So proportionality constant, we can insert some proportionality constant as k. So we have minus di by dc, which is equal to ki. So you bring this I term to this side, we have minus di by I, which is equal to k dc. On integrating on both sides, we have minus di by I, which is equal to k dc. So we have the integration of minus di by I will give us minus ln I, which is equal to kc plus b. B is the integration constant. When c equals 0, there is no absorption. So I becomes I naught. Substituting in this expression, we have minus ln I naught, which is equal to k when c equals 0 plus b. So b, the answer for b is nothing but minus ln I naught. So we have, substituting in this expression, we have minus ln I, which is equal to kc minus ln I naught. You bring this term to this side. So we have ln I naught minus ln I, which is equal to kc. And of course, we know log a minus log b, which is equal to log a by b. So we have ln I naught by I, which is equal to kc. Your I naught by ic, which is equal to exponential to the exponential kc, e to the power kc. And I by I naught, that is just to invert it, we'll have I by I naught, which is equal to e power minus kc. So I equals I naught e power minus kc. We'll solve one problem. In a sample with an absorption of 1 at a specific length, what is the relative amount of light that was absorbed by the sample? The definition of absorption is given as A equals log based on I naught by I, and the relative loss of intensity is given as I minus I naught divided by I naught, which is equal to 1 minus I by I naught. So equation 1 can be written as 10 to the power A, which is equal to I naught by I, and just to invert both the sides we'll have 10 to the power minus a, which is equal to I by I naught. Then you add 1 on both sides, we have 1 minus 10 to the power minus a, which is equal to 1 minus I by I naught. We are going to subtract 1 minus on both sides. So substituting has given us A absorption equal to 1. So A equals 1. You substitute, we'll have 1 minus 10 to the power minus 1. That will give us 1 minus 1 by 10, which is answer as 0.9. So this is the relative amount of light that can be absorbed by the sample. Lambert Bouguer law. This law states that when a beam of light is allowed to pass through a transparent medium, the rate of decrease of intensity with the thickness of the medium is directly proportional to the intensity of incident light. So let I be the intensity of incident radiation and T be the thickness of the medium. Then we have minus di by dt, where T is the thickness. It is not time, it is thickness, which is directly proportional to I. So proportionally constant, you just insert, so that will give us K times I. Then you bring this I term to this side, left hand side, and dt to right hand side. So we have minus di by I, which is equal to K dt. Integrating on both sides, we have minus di by I, which is equal to K dt. That will give us minus ln I, which is equal to Kt plus B, where B is the integration constant. At t equals 0, there is no absorption, so I becomes I naught. The absorption implies that the intensity is decreased. Absorption depends on the thickness of the medium. So we have minus ln I naught, which is equal to K. Instead of substitute t equals 0, so K times 0 plus B, so B equals minus ln I naught. So substituting minus ln I naught into that expression, minus ln I, which is equal to Kt plus B, we have minus ln I, which is equal to Kt minus I naught. You bring this term to left hand side, we have ln I naught minus ln I, which is equal to Kt. So we know that log A minus log B, which is equal to log A by B. So ln I naught by I, which is equal to Kt. Just invert it, that will give us I by I naught, which is equal to e power minus Kt. So I becomes I naught times e power minus Kt. The Beer-Lambert law is widely used in various fields, including spectrophotometry, measuring the concentration of substances in solutions by determining how much light they can absorb. Biomedical optics, determining oxygen saturation in tissues, bilirubin levels in blood, and hemoglobin concentration. Environmental monitoring, measuring pollutant concentrations in water and air. Limitations. The Beer-Lambert law is the most accurate when solution is dilute. The light source is monochromatic and there is no scattering or reflection of light. In some cases, such as with biological tissues, scattering can significantly affect the accuracy of the law. Transmittance, absorption, and molar absorptivity is the last topic in this section. The first one is transmittance. It is defined as the ratio of the intensity of light transmitted by the sample, which is denoted by P, to the intensity of incident light, which is referred as P naught. It is expressed as a percentage with 100% meaning no absorption and 0% meaning complete absorption. When the radiation is passed through the solution, here, the radiation which passes through the solution and comes out of the solution is known as transmitted radiation. So, as the definition goes, and we have T equals P divided by P naught, which is usually represented in terms of percentage. So we have transmission, which is equal to P divided by P naught times 100. It has values from 0 to 100. As the concentration and length of the solution increase, the absorption will become more and more, and hence transmittance decreases. So transmittance versus length is drawn here. As length increases, the transmittance decreases, and here also as concentration increases, the transmittance decreases. Absorbance. It is a measure of how much light a sample absorbs at a particular wavelength. Certain radiations which are absorbed by the molecules of the solution is called as absorbed radiation. A logarithmic measurement of how much light is absorbed by a substance, also known as optical density. It is defined as the log of reciprocal transmittance mathematically, and it is expressed as A equals log 1 by T. So this can be written as T to the power minus 1, log T to the power minus 1. You bring this minus this side, so we have minus log T. So we'll have to use the expression for T equals P divided by P naught. From equation 5.20, we have minus log P divided by P naught. Of course, when length increases, the absorption increases, and the concentration increases, the absorption increases, as shown in the figure. So we have log P divided by P naught. Just to bring this minus to the rise to the power, then we have P divided by P naught to the power minus 1. So which is nothing but A log P naught by P. If we increase the length of the medium and the concentration of the molecules, then the more number of molecules will absorb the radiation. Hence, there is an inverse relation between absorption and transmittance. As the amount of light absorbed increases, the amount of light transmitted decreases, and vice versa. Thus, A equals 0 indicates that 100% of light has been transmitted through the sample. The specific wavelengths of light absorbed are characteristics of the substance, allowing for its identification and quantification. The last item is molar absorptivity. It is defined as the proportionality constant which relates the absorptions A at a particular wavelength lambda to the molar concentration C of the sample and length L of the path of the light beam passing through the medium. So A is directly proportional to length and the concentration. So L into C. So A equals some constant sigma times L into C. So sigma equals A divided by LC. The unit will be liter per mole per centimeter. And of course, we have we can come to know the units easily. Liters, mole inverse, centimeter power minus 1. The corrected absorption value is called molar absorptivity, and it is particularly useful when comparing the spectra of different compounds and determining the relative strength of light absorbing functions, chromophores, what we call this as. Molar absorptivity, also known as the molar extinction coefficient or molar attenuation coefficient, is a measure of how strongly a chemical species absorbs light at a given wavelength. It is an intrinsic property of the substance and indicates the likelihood of an electronic transition occurring when light of what wavelength interacts with the molecule. The molar absorptivity of a substance refers to its capacity to absorb light of a specific wavelength. In addition, a higher molar absorptivity means the substance absorbs light more strongly at that specific wavelength. A high molar absorptivity indicates that the substance absorbs light as well as at a given wavelength. Intrinsic property. Molar absorptivity is a characteristic of the molecule itself and does not depend on concentration or path length. Electronic transition, it represents the probability of an electron being excited to a higher energy level when absorbing a photon of the corresponding wavelength. Beer-Lambert's law. Molar absorptivity is used in the Beer-Lambert law to relate absorption, concentration, path length, and molar absorptivity. The law states that absorption is directly proportional to the both concentration and path length, and proportionality constant is the molar absorptivity. Units. The units of molar absorptivity are typically liter per mole per centimeter. Determination. Molar absorptivity can be determined experimentally by plotting absorption versus concentration and finding the slope of the resulting linear plot. So there will be a linear plot, just take the slope. That will give you molar absorptivity. Relationship to other terms, absorptions. molar absorptivity along with concentration, and path length determines the absorption of a solution at a given wavelength. Extinction coefficient. Molar absorptivity is also known as the extinction coefficient. Thus, the amount of light is absorbed by a sample at specific wavelength, which is then used to identify the presence and concentration of different substances within the sample. The technique relies on the principle that molecules absorb light at specific wavelengths, which corresponds to electronic transitions within the molecule.